to SAGES for the opportunity to present this work. I have several disclosures. I'm on the board of a couple of for-profit companies and one consulting firm, although none of them have anything to do with this work. I'm going to take you on an 8-year journey. All of this work was funded by government grants, the first from New York State and the subsequent 2 from the NIH. We based the work on the premise that robotic technology has the potential to improve minimally invasive surgery and that currently available robots don't really provide value, even if they may provide good technical performance, maybe even if they improve some outcomes, but the cost really is very prohibitive at in the current state for most procedures. So we designed our device starting with the imaging platform to overcome all of these constraints with either laparoscopy and even with current robots. I mean, the current robots may have given us a 3D image and solved this, but they still have issues of limited mobility of the image source on the inside, and it occupies an incision for the duration of the procedure, and you can't use that incision for anything else. Same thing with the tools. There are problems with the tools that we use in standard laparoscopy, and there are problems even with the tools in the currently available robots. So the first thing we did was design an insertable camera system, and this was done with grant funding. And we made it so that it could either be 2D or 3D. Here it is in the middle of construction. We have a ring of LED lights around the CCD chip and lens, and then motors back here that allow it to pan and tilt. This shows the software that allows the camera to track whatever you want it to track, so you don't need a human being to control it. And it can be made still when you want to focus on something, but if you want it to move around, you simply move your instrument and it will follow you to the point where you want to work. This is obviously in an animal model with just the camera following the instrument over the top of the liver. So the second part of the project with the second grant was to add tools to that, and the grad students in the engineering school came up with IREP, the Insertable Robotic Effector platform. And this was simply to add any of a number of types of tools to the insertable camera, retain remote control, and ultimately enable automation of certain tasks. And it was this that made us want to control all of the tools with motors rather than direct drive, so that the computer could actually do it, and using sensory feedback data from the sensors, tie knots, for example, to a certain tension with quantified information. The reason that we got the second grant was because of this drawing, and so this is a 15-millimeter diameter tube that we could insert into the abdomen. Once inside, then it would deploy 2 cameras, one here and one here for stereoscopy, and then this would fold out and have 2 snake-like arms on which we could put tools. Once we were funded, then the design really changed some, and it came to look like this for a while, and then ultimately it looked more like this, with the stereoscopic imaging source above and between the 2 arms, kind of like the human body's made. So this is an animation of the CAD. It's not just a cartoon. We probably wouldn't put the tool in through this site, but once inside, wherever you put it through, umbilicus or a natural orifice, then it deploys the stereoscopic camera system, which has pan and tilt and has the automatic function that I described for you a minute ago. We separate the 2 arms by 4 centimeters, so we have triangulation. And the 2 snake-like arms have each 2 segments with up to 6 vertebrae put together to give, in total, 21 degrees of freedom. This is just another view of the same device. And then there's 180-degree rotation of each tool. There's the camera unit from a different view. There are the snake-like arms, and they are on what we call the parallelogram, which come out of the shaft after it's placed into the body cavity. There are 5 backbones. The primary backbone does not move, But the secondary backbones, all 4 of them, are attached to the end discs, and using the actuating motors on the outside, they can move these and bend the snake in any direction. We did studies on me doing operations and created the sphere, or calculated the sphere in which my left hand or my right hand moved, the sphere in which my left hand moved, and the space in which we were going to do the operation, and then we made the snakes so that they would cover this common overlapping area completely. The jaws had to be built so that they would hold a needle without twisting, so that we could suture with it. And you can see how intricate this is, so we've had a little delay in constructing the second one. And here it is, again, the overview of it. Believe it or not, we are now nearly completely constructed with our prototype. Here's the camera module. Here's one completed snake. The other snake, we're still waiting for the machining. We've had a delay in machining of some of the components for the second gripper. And when I submitted the abstract, I thought I would be showing you that I could suture with 2 hands on this. But because of the lack of that gripper, we're not there. The motors are here in the schematics or in the CAD, and here are the motors in reality as we have constructed it. Here's the schematic, and I know I'm running out of time, the schematic for the controller board and the computer. And then these videos simply show a more recent level of being able to track. And the computer can absolutely fix on the gripper of this is our real device moving out in space. Here we trialed it just in a video of an nephrectomy. Next slide, please. And this just shows that it does have the motions that will allow us to suture. So, next slide. In conclusion, why are we doing this? We think we can reduce the invasiveness of procedures. It's a much smaller overall package. It should be much less expensive. And all I've really shown you, for the most part, is the hardware. And in my mind, this is not about the hardware. We have to have the hardware to do it, but the real benefit of this is in the software that will allow us to automate tasks such as suturing and tying to certain tension, and ultimately to give us technical decision support and guide us as to what we should do next in an operation. Thanks.